So in the last video, I hooked up all of this stuff, all the different peripherals that I've been building up, and things are working pretty well there. I did get my crystal upgraded to an 8 megahertz, so I'm running at 8 for the moment. And I'm now going to start diving deeper into all of the different assembly coding. I have assembly coding to work more with whatever I connect up to the VIAs, a ton of video work, VGA type of work, and other things as I go forward. But I thought as I get into that, debugging, it's rare that I ever write code that works correctly the first time I write it. So debugging is always an important part of what I'm doing. And right now I don't have, or I didn't have prior to today, a good way to maybe get out debug information. Now I've got this little 2-line LCD and it's adequate. I can put out some stuff, it's helpful, but there's limited space there and I have to really pay attention to where am I on the screen, clear the screen, or scroll things, and it's not a lot of real estate for debug information. So I thought what made the most sense is to try to get connected over here with this white cord, my USB-C connector, and do USB-C serial or USB serial communication. And that way, from within my code anywhere, I can write things out to that serial and maybe even allow the user to interact through a terminal, much like the built-in ROM on the 265 does. It has that built-in Mensch monitor ROM. That lets you, interrogate the values of different things, write new values, etc. Well, that's what I'm going to do in this video. And if I back up here, this little board that I was using before, this is the WDC, it's the 265 SXB board. And it has a little USB, a micro USB here that you can plug in. It has the FT232 on it, and then I can do serial communication on UART number 3. That's what it's basically hard-coded to do, is UART number 3. Physically, it's hooked up that way, and then the ROM is set to use that. It's also hard-coded at 9600 baud, or maybe BPS, bits per second, more accurately. So it's running at 9600, which is pretty slow, but for what it's doing, it's fine. But instead of me using that, I boot up to my ROM. So I start with the built-in monitor ROM, and pretty quickly I jump over to my external flash and completely hand over control to the code there. That was on this board. This board down here is the same thing. It's just I'm using a different format of the ROM chip. It's a DIP instead of that PLCC format, which, by the way, is absolutely awesome compared to that other board. I can pop this in and out so much easier. My board that I have here, I followed their example of their board from WDC, and I also hardwired it in for UART number 3. But I now want to put in the code to use that UART 3 through that USB interface so that I can write out to it and maybe read back things that the user might type in or do with the system. So that's what I'm going to dive into. And this probably won't take too long to go through, but I'll walk through the code that I have really to make this work, kind of give you a feel for that. And I've kind of stubbed in the basics, and I have a lot more work to do here yet, but this might be basic enough that if anybody's trying to get maybe even back on this board, your own monitor, your own ROM working, and you want to use the USB serial, what I go through here will help you get that up and running without relying on the one built into the 265 itself. Maybe one quick note from previous videos, as I was connecting maybe this VGA card early, or maybe in this last video as I went up to 8 megahertz, I was seeing a couple pixels show up in spots maybe that ideally shouldn't be there. Tracked that down. It actually ends up being, I commented on this when I hooked up this video card, is that I was only running a single line for 5 volt and ground from this board over to my board, my main 265 board, and that didn't seem to be enough. So I ran 2 more pairs. So I have 3 VCC lines or 5 volt lines and 3 ground lines going between my board and this little ISA expansion type of card, which then feeds the little VGA card here that I have. And that took care of all the pixels showing up when maybe they weren't supposed to be. It was kind of a random here or there type of pixel, but seems to be much, much better now. I don't see that at all. So just a note on that, if you're curious if I ever track that down. Let me, on my screen here, this is the board, my board, of course, and of course I've got my 265 here. I'm using this FT232RL to connect to it, and then really running that out to my USB-C connector. And if I want to look at the schematic for that, this there's not a lot there, as far as that FT232. It's connecting up here. You can see there's 4 pins. So it's port 6, pin number 6, 7, port 5, pin number 7, and 6. So those 4 pins are used to connect to the 232, and then the 232 just simply has a pair of data lines that go out to the USB-C connector with this little chip in the middle to do some protection of those lines as far as voltage spikes coming in or anything like that. So that is, hardware-wise all there is, but, you do notice that these 4 lines are really hardwired into, these locations, which is all for UART number 3. And that's what I'm going to be working with here. I'm going to set that aside, really not use much of that. As far as easy EDA, that's probably enough for today. But what I am going to jump into is code. And let me get my code up, which looks like this. Let's walk through the code that I have here, and I'm going to talk through what does it take to get that COM3, or not COM3, but UART number 3 running. And it happens to be on the PC I'm on, it is on COM3, but that's just how the PC detects it and where it fits in its lineup of COM ports. As I go through this, I'll point out the key sections, and let me first, before I do that, kind of show you the result of what I got to. And I am using TerraTerm, and let me flip over to TerraTerm right here. And here you can see, my system right now, it's on, LCD's initialized, my VIAs are coming up to the default values that I write to them, keyboard is initialized, all that. And you see my COM3 here. Now my COM3, if I go into that serial port, I am running at 125,000 bits per second, so 125K BPS. And what I am going to do now is I'm going to just turn off my system because I had cleared that screen, and I'll turn it back on. And what I do during the first cold start is I actually write out to the serial that initialization is complete, welcome, and then I had just as a test written out a value that it pulled from the A register, and I write that out in hex. The other thing I can do now is I can go into here and I can press the H key on my keyboard, and it will come back with some help information. And right now I don't have any of this implemented, so I can't yet modify a byte or dump a byte, but that's not going to be too big of a deal for coding now that I've got this kind of a skeleton put in place. But what it's allowing me to do is from the system here, output anywhere in my code serial data that can show up on my PC, and from my PC, when I press keys, it generates an interrupt that my system can then process. And in my case, it's looking for the H key is the only thing it's looking for right now. If it sees the H key, it dumps out the help menu. But then I'll eventually add, modify and dump and, some other types of things that you would have seen on the built-in monitor ROM from WDC. So to do this, let me run through the assembly to make that happen. And back over to here. Okay, so here is my code. I'm going to scroll up to the top and just point out a few sections as I go through this. And I will get this posted, so if you want to go through this code, I guess, in more detail, I will have a link in my blog page for this project. Plus, of course, it's out on my GitHub, so if you get out there, you'll find it pretty quickly, I think. But I'll link it so it's easier to get to. Let me run through. Let me scroll down. I did add a section of equates down here. And so this is to get my UART, what is the address? Like many of these devices I'm working with, there is a register or a series of registers to work with the device. There is a control register, and it is at this DF76, and I've used this label of ACSR3. Now with all of these, I can jump out to the data sheet, and if I want to come out to the data sheet, I can do a search, and I can look for ACS, and I'll find this asynchronous control and status registers, and then I can see that there's a series of status registers, one for each UART. I'm using UART 3. They talk about it and talk about a data register, this ARTD, and then I can kind of keep on going here. There's also this ACSR, so asynchronous control and status register. And so this is at address DF76, and that is what I'm going to be using here. And that lets me control these settings by changing certain bits there. So then there's the data register. There are two registers related to interrupts. So there's an actual interrupt enable register. You can go back to my interrupt videos. Very similar to EIER that I had previously been working with in videos, but now it's UART interrupt enable register instead of an edge interrupt enable register that I was working with previously. And then there's a flag register to tell me if an interrupt has occurred or not. So then there's going to be certain bits that I'm going to look at. If, for example, here I have this interrupt flag register that gets used to track if certain things happen, like my transmit is full. So I'm going to use this to basically check as I'm trying to send things. I can't send things too quickly, so send something and then I have to do a delay, but you'll see some of these later in code. I don't think I'm using the receive full yet, but I think I am using this transmit full. And those are things I can look up if I go look up this UIFR. And coming over here then, UIFR, I'll just search the data sheet. I think it should find that. Let's see, there we go. Interrupt flag registers. EIFR is one I've used before. TIFR is a timer one, but let's get down to the UIFR. And so it has this address of DF, let's see, DF48. And if I keep searching then, I can get down to interrupt flag registers, and there's the timer. Here's the edge, and then if I keep going, here's the UART. So there is a UIER. This is where I can enable interrupts, and you'll see me do that later for the third UART receive. And then if I keep going down, there's also this UIFR, and that's going to let me know if I have basically read full, or I believe this one is a transmit full, even though it's not labeled consistently like the others, but that'd be a transmit full. Or at least that's how I'm using it. I believe this here probably should say U3TF to be consistent with the rest of these. Maybe it is different, but again, this is one of those documentation quirks that you're going to find a whole bunch of in this document, unfortunately. And then this is also UIFR is actually at DF48, not DF47 that the document is showing. So be careful for that. So UIFR here, it is listed incorrectly. This is yet another pretty major typo in this document that is quite old, and I don't know why those haven't been updated. Maybe it's because people don't use this document and don't use this microcontroller, but things I'd expect to have gotten updated. By the way, as I find those types of things, I am putting them at the bottom of my blog post of just little mistakes I'm seeing in there that really will cause you a lot of problems. If you were trying to use DF47, you're not going to get anywhere here. Because DF47 actually is back on our, I believe that was DF47 EIER. Yeah, that's EIER is DF47. So totally different interrupt, and that's not helpful that the documentation doesn't list it correctly. So I put all those in here though, so I'm just setting up pointers or just references so I know that this list friendly name is at this address, and I've got those all set up and good to go. I am also going to have to use timer number 3. And this is to set up the baud rate for communication. And so there's a low byte and a high byte that I'll have to set, and you'll see that in my initialization code. So then I'm going to scroll down. With those in there, I can get into my start code, which I've cleaned up a little bit. So as I get into this, I did add this a little delay. So there's a delay routine that I put in, and really it just gives everything time to fully settle. And what I've noticed is if you turn the system on and try to start writing too quickly to a UART, it doesn't work. But if you give it a little bit of a delay, it'll work fine. So there's some time it must take, a certain number of cycles before it's up and running. So I put in this little delay procedure. That's all this is it just kind of says, just wait here for a little bit to give all the peripherals time to come up. And I found that to be really helpful, both for my PS2 keyboard circuit and for the UART circuit, or the UART functionality in the chip. That's been a good thing. Then I go through configuring the microcontroller itself, and I think all this stuff is stuff that was in a previous video, or this is built up over the videos. So you can look through that. That's basically just getting everything set up. Well, maybe one thing I would point out though, right away I turn off all of the interrupts around timers and UARTs and edge. And then as I go through my initialization, I turn on just the things I want to turn on. Because control was handed over from the built-in monitor ROM, and I don't know, and I didn't want to go reverse engineer all that code to figure out what did it turn on, what is it using, if anything. And I think it is using things, so I just said turn it all off, and then I'll only turn those back on as I reconfigure them. And then I have a procedure to initialize the UART, initialize some other interrupts, initialize my keyboard, the VIAs, my LCD. So all of that I basically come in here and do. And this code I'm going to take out, I don't need. And then I fill my screen with black, in other words, clear the screen, and then I fill in some test color bars like you saw in the last videos. And then I get into this main loop where I just sit here and spin basically and have it do, some standard housekeeping like checking for new keys and things like that. But what's of interest probably today is this init UART3. So if I go down, here's my init UART3 procedure. I shouldn't need this line, but I am putting it in here just to kind of remind myself I need to stick to 8-bit code for this, or set this differently, but right now I'm setting it to 8-bit code. 8-bit A registers, 8-bit indexers, etc. Then I have to set up my timer, and right away I tell it that I want to use timer number 3. I think you have one other option, but this is in something called a TCR. And so again, datasheet is our friend here 95% of the time, but then I can get in and configure this TCR. I'm just going to see if I can find the bits on it quickly. So this is a timer control register, and here's the address, and here's where I can configure timer information. And so this I'm coming in and saying, well, I want to AND it with a 0 and all 1s. In other words, keep it all the same except for this highest bit, set it to 0. And so that says use UART3, timer 3 is selected for UART3. If it was a 1, I'd be using timer 4. So I'm using timer 3. That's what this is doing here. And then I have a few different options I've been just kind of testing with of what speed do I want to run at. And initially, just for a safety set, went down to a 6 megahertz clock, and I configured it for 9600 BPS. And with that, I needed a value of 38. And they give you calculations on how to calculate this in the data sheet. So you can do that, and you basically have to take your actual clock speed, whatever you run Phi 2 at, as part of that equation. But this 38, I'm not going to go through the math, take a look at the data sheet, but if you look at this will run at 9600-ish, close to that, for a 6 megahertz clock. If I wanted to go up to another decent option on a 6 megahertz clock, 115-200 would have been my next thought, is to go to that. But that is a little bit off. With an 8 megahertz clock, this system can actually generate the right speed of timer, or the right frequency for this 115-200. So instead, though, you can get to a 125, and it seems like that is maybe somewhat common out there, that people would jump to 125, and that's what I did some testing with, and here's the values I would use to get that. Right now I have the 8 megahertz crystal back in, and so I want to run at 125. That works out well, and I set the value to 0003, but that will basically configure this timer to run my UART at 125 BPS. Then I have to enable timer 3, and so there's a little enable register, so timer enable register, and this is turning on timer number 3, since that's the one that's going to get used for this serial communication. And then I have to configure how I want this to communicate, and I'll jump over here, and while I'm searching for this, you can look here and see that I'm setting it to 8-bit, no parity, and enabling both receive and transmit. And I should just be able to come in here and search for ACSR. Okay, let me get to just the bit definition for those. So here are those bits, and so I'm doing the lowest bit, which says enable transmitter. I'm using the 2 bits up from that. That would be transmitter, receiver, send, and receive 8-bit data. And then I jump up to this one, enable the receiver. So those are the 3 that I am turning on. So that's the 8-bit, no parity, receive, and transmit enable. Then I have to enable interrupt. And in this case, I'm going to go look up this UIER. Again, UIER, I can go into the data sheet and find what do the different bits for that do. And we get to that table. So here's our UART interrupt enable register. And second to last, so bit 6 here, I'm enabling it for UART number 3 receive. So if I receive data on UART 3, I want it to basically raise an interrupt, so I can do some processing inside of an interrupt service routine. And that's it. And so at that point, I should have a functional UART number 3 and should be able to communicate to my PC. So then I have a routine that I put together here, UART 3 put string or puts. And so that lets me write out a string, and it's going to write out whatever string is at this location called strptr. And so if I want to search for that real quick, I have, went over it. This here, I just had set aside up in my 0 page or direct page, I set aside 2 bytes to store that pointer. And then here I'm saying fill in that pointer with whatever point to this string here. And this string is byte data, and it starts out with a new line or a carriage return line feed along with initialization complete, welcome. And if I go back to my Terra term, that was the output that you saw here when I turned on the system, initialization complete, welcome. And that's what this little block is doing. It's just saying take that and write it out. And then I have a procedure called carriage return line feed, which just simply sends out a carriage return and line feed out to the terminal. So nothing too exciting there. And then I put out another string, string print reg A, and it says it's going to write out reg A current value of something. Well, what it's going to write out is whatever's in the A register when I call it. And that's going to be done down here with this hex print serial. So I've got a routine that will take a value, whatever's in the A register when you call it, and print it in hex. And I load up an AA, hex AA, just as a test. And this is temporary code that will come out after this video, but I just wanted to be able to kind of show how would you read a value. And then in that case, I'm reading the A register. If I wanted to read something else, I would just simply transfer it to the A register, load it into the A register, and then call that routine, or call that routine hex print serial many times, depending on how much data I was going to print out. I've got some supporting routines for all of this. So there is a transmit So whatever's in the A register when I call this UART3 transmit will basically get sent over the serial. So I load up this flag register, and then I have to, within that, read one of the bits. And I'm going to go back to the data sheet and UIFR right here. And so in this case, U3TF is, I've got it set to this highest bit, bit 7, so that's equal to a 1 and 7 zeros after it. This, I think I would have expected to see U3TF there, but that's the one I'm reading. So if anybody has insight that that's wrong, or that this is really should say, for uniformity here, U3TF, just like all these others on the way up do. But I'm going to read that bit, and I'm looking to see if that bit is set to a 1. If it is set to a 1, then I have a loop basically. So and it with that 1, you know, if it's equal, wait. So just keep waiting here until it's clear to go. So then once I'm clear to go, then I continue to move forward, and that's where I then store whatever was in the A register coming into this routine out to ARTD3, and that was the data register. So I write out the byte of data to that, and that's what sends it out through the serial. A couple of delay routines, the carriage return, line feed, and then there's a hex print serial. You can look at those if you're interested. I'll put the link up there. And then here's this put string, and all the put string does is it runs through a bunch of bytes until it hits a 0 terminator. But it basically then for each of those calls the basically the routine to actually write out the character. So I had a string of 20 characters. It's going to run through this, print each of the 20 by calling this UART3 transmit. And that's it for routines on the serial related. Now, if I go back to here again, let me just hit reset and see if this comes back up. So there, you know, I did its delay, and there's what I see when I initialize. If I go to my keyboard on my PC right now, because I'm in the terminal, I hit H, you know, I got that output. Well, for that to work, it had to run the interrupt, which means in my code, I had to set up a vector for that interrupt. In previous videos, I've done this negative edge 64. I've done IRQB. So you can go back and watch those videos when I set those up. But in this case, I need to set up a new handler in this vector. And it needs to point to, basically, this needs to be at FFAC. Now, right now in this code, I tell it 1 FFAC, but when I actually boot my ROM, the location it shows up at to the system is FFAC. So however you get your ROM mapped, and in my ROM, just as a quick reminder, you can go back to I guess older videos that talk about this a little bit, but in my ROM, it's 128K ROM, but it's the last 32K that actually needs to store. It kind of banks it. It's like 4 banks of 32K, but you need to put your ROM at this location, hex 18,000. And if you want it to boot straight to your ROM, you got to put in this WDC character. But that's why all of my stuff here at this 18,000, when it actually boots the system, it's mapped as 8,000. And so if I want an address of FFAC, I'm actually going to put in 1 FFAC, and that's going to get me to the right location. However you have your ROM set up, though, you just need to make sure that this is how you're doing it. And whether you're using, you know, like my board is doing the exact same setup as this WDC board. So out of this chip, 128K, it's the last 32K. That's where you need your interrupt vectors, is in the end of that. But when it boots up, it sees it as a slightly different address. But I'm saying that at FFAC, when it's running, if it runs into basically this UART3 receive, I want it to run this procedure here. And if you want, again, you can go to the data sheet. And, I think this is early in the data sheet. Let me see if I can find it. They have tables. Here we go. So we've got priority encoded interrupt vector module. This is for emulation. I'm not doing emulation. I'm doing native mode. which is what the WDC would be using by the time you get into your own ROM. It's in native mode. And I can see that there's a UART3 receive interrupt FFAC. So that tells me the address it needs to be at. And that's what I've got going on right here. So that then, if I receive something through the serial, is going to run to this interrupt service routine. And let me get up to that interrupt routine. It looks like this. So this is having it just read whatever byte of data was received. So read that data register. If it was a lowercase or an uppercase, go down to this and run it. Otherwise, jump down to done. And so if it was, I put in a lower or upper H, then it's going to print out that string of whatever is in this str serial help. And if I go to that, that just simply says write this out on a line, carriage return line feed, second line, carriage return line feed, etc. And then you saw that ultimately here look like that. So then I could have it flip flags or stay in a loop asking you for more information. But at this point, the processor has gone back to doing its normal thing. So, if I come over here to my LED and I have my keyboard, I can start typing, and it's processing that, and that's not sitting in some loop waiting for serial input. The serial input is on an interrupt. The keyboard input is on an interrupt. So I think that's a nice way to do all that, and it's kind of probably the standard way. The alternative would be to run some type of polling loop, and that's not what I wanted to do. So I think that is pretty much it. Again, I've got to set up some stuff in my initialization. You can go back through that code at your leisure. And I have a whole bunch more supporting routines to build up, like writing out, bytes, multiple bytes, let's say 2 bytes at a time or 16 bytes at a time, etc. And then after that, it was the interrupt setup. So coming in here, adding in the handler or the vector to point to my handler, and then putting in something here in the handler that's actually going to do something with the keys as I press keys. And I imagine that's going to get more complicated because in some cases I'm going to have to type in multiple keys in a sequence, and not until I press enter and see the enter key do I actually process it as a command. I've done a little bit of that on some previous systems, so I'll have to kind of set up this, buffer to capture those characters and look for the enter key, and then see if I can determine what to do based on what the user typed in. So then the result at the end of the day is that I can write out to serial, and I have interrupt set so that if a user interacts with that serial connection, sends something back to the microcontroller, I can do some processing based on it. So I will get this current code as it sits posted and take a look at that. If you got questions, comments, do drop a note below here on YouTube. Appreciate everybody following. Thanks.